it's a problem because a lot of people do want their Flash. I mean, we're working with the Voice of America people, and they're an actual news organization, and they have to provide YouTube things because nobody else, I mean, nobody wants to read text anymore. They all want to watch little video stuff. So if we're trying to provide circumvention around firewalls, we have to let them watch their YouTube or they get upset. So how do we actually fix this? Turns out it's easy on every operating system other than Windows. So it's a one-liner in IP tables or PF. You just say, all the stuff that's going to go out as TCP, send it to this port instead. And then there's an easy system call, and you say, that connection you just gave me, what was its destination really? And then you just swap it in, and you make your connection, and you're all done. Windows is a little bit messier, but we've got a couple of solutions we're working on. One of them is put a Tor client inside and a Linux kernel inside a QEMU and run that on Windows and intercept all the outgoing connections. So we actually have Linux with IP tables and the system call we want and so on, and it just intercepts all outgoing TCP and shoves it into the Linux plus Tor. And then it turns out it's even faster because Tor performs better on Linux in QEMU than it does in Windows. But I'd like to fix that at some point also. So there's another approach, which is let's put more stuff inside the QEMU. Let's put our Linux kernel, and let's put the Tor client, and let's put Firefox and Pigeon and a few other things and get them configured correctly. And then people just click, click, and it pops up and it has everything they need to have secured and configured, and it makes sure that all the packets go the right way, and when you close it, it just goes away. So the middle one, the one we're working on is called Tor VM. The bottom one, there's a live CD called Incognito that you can boot inside QEMU, inside Windows, and you've got your whole live CD with all the applications configured right. Okay, so what are some other challenges that we have to tackle? One of the big other ones, I was talking about circumvention or censorship resistance. There are a bunch of different ways that you could block the Tor network, that you could block connections to the Tor network if you wanted to. One of the easy ones, there are 6 directory authorities that I talked about at the beginning of the talk. Their IP addresses and their keys are hard-coded in Tor. So you just go look up those 6 IP addresses, you put them in your national filter, and you're done. No more Tor for your citizens. And if that doesn't work, go fetch the whole directory, and there are 1,500 IP addresses in there, and just put all 1,500 into your network filter, and now you're done. Another option is if you can figure out that the encrypted connection you're seeing is a Tor connection, then you just hang up on it. You say, that's not really SSL, that's a Tor connection. We've mostly fixed that one at this point, but there's still an arms race. We're trying to look a lot like Firefox talking to Apache, because hopefully there are a lot of Firefoxes in the world and a lot of Apaches in the world, even inside and across the Chinese firewall. And then the fourth approach is just block the website and then hope that all the people inside your country say, well, shucks, that was good while it lasted, but I guess Tor's gone too. So the design we've been working on, and I talked a lot more about it here 2 years ago, is a system called bridge relays. So the idea is rather than having just those 1,500 relays that you can choose from, instead for your first hop, give all the different Tor users an option to say, I want to be a relay, but not in the public list. Don't put me in the big list of 1,500. Put me in some separate list that you don't give out all the addresses for. So now we've changed the problem from how do we keep 1,500 public IP addresses out of the hands of the Chinese government, which is an impossible problem, to how do we collect 10,000 or 30,000 bridge relay IP addresses from Tor users who want to help out. How do we collect those 20,000 and give them out one at a time to the good guys without letting the bad guys learn all of them? And that's still a tough problem, but it's a little bit of a more straightforward arms race. And I'd be happy to chat with you more afterwards about how that works. Okay, so those were some of the practical issues. I'm a little over halfway done, is that true? Time-wise? I think so. Okay, so there are a bunch of academic research things we should talk about also. Here are a bunch of different ways that you can break Tor depending on what level of abilities you have and where in the network you can look and stuff like that. The most straightforward one is traffic confirmation. I talked about that at the beginning. If you can watch Alice's connection or the connection at the first relay, and you can watch Bob's connection or the connection at the last relay, then you can do some very simple math and start saying, hey, I bet these line up. And there are some research designs for how to defend against this. There's one called defensive dropping in 2004, where you send a bunch of extra packets, and then they disappear somewhere along the path. So the set of traffic going in looks quite different from the set of traffic coming out, because not all of the traffic makes it to the end of the network. A lot of it gets dropped partway through. Another design is adaptive padding that came out a few years ago from a fellow who's now at UTexas. And the idea there is to look for gaps and try to fill them in. And that way it'll be a little bit more uniform and a little bit harder to figure out which incoming flow matches which outgoing flow. Unfortunately, the attacks in this arena are usually a lot more effective than the defenses. There was a fellow named Stephen Murdoch, who's actually a Tor developer. A year or so ago, he published a paper at the Privacy Enhancing Technologies Symposium on how do I just do sampled traffic analysis. Let's imagine I'm an internet exchange. Let's imagine I can only see a very small fraction of the packets, 1 in 1,000, 1 in 2,000. And even if that's all I get to see, here is the math that lets me line up which incoming flow matches which outgoing flow. So if you drop more than 99% of the packets, I can still figure out which one coming in matches which one going out. That sucks. So I'm not really very optimistic about fixing this, which means that the way we defend against this, the only way Tor can defend against this, is to grow a large enough network and a diverse enough network that not very many people can see the traffic on this end and the traffic on this end. If you have a better answer, I'd love to chat with you. Another fine attack, website fingerprinting. So there are a bunch of papers in academic conferences saying, if I get to see an SSL encrypted link, if I get to see you doing a connection to some website using SSL, I can guess just by the timing of the packets and how many bytes there are, which website you're looking up. The way it works is I make a list of 1,000 websites I think you're going to, and then I look at the bytes I see on the network and I try to match them up to which website it is. So that means, first of all, I can get a good guess about where you are going, and second of all, I can narrow out a lot of places that you might be going to. Does this attack work on Tor? I have no idea. I've talked to a lot of researchers who say, oh yeah, I started doing the research paper on it and I set up the attack and I tried it and, you know, I'm not really sure if it worked. And nobody really says, no, it doesn't work, and nobody really says, yes, it does work. So part of the reason why it wouldn't work is Tor blocks the bytes that it sends back and forth into groups of 512 bytes called cells. So the fact that we're chunking things up into groups of 512 bytes confuses the attack. Surely the attack will still work, it's just that nobody who's tried has actually made it work. So that's kind of bad, but not really bad, but maybe it is bad. I don't know. And you can actually probably do a more effective version of the attack by looking not just at, I think this is the front page you looked at, but build a map of the front page of each of these websites and the most popular second links. So now if I see you do some anonymous lookup, and then I see you do a second anonymous lookup, I should say, which websites match both of these page loads? And at that point, I should be able to narrow it down a lot faster. Another messy attack that we're still trying to grapple with, called the clogging or congestion attack. So in 2005, Stephen Murdoch and George Danezis published a paper on a low-cost traffic analysis of Tor. And the idea was, there were only 15 relays at the time, so it was a bit easier. You build a circuit from you to each relay and back. So you have 15 circuits, and you're sending constant rate traffic down all of them. And then when Alice goes to the website and fetches a page, you run the website. So you dump as large a page on her as you can, and it produces a big bump in 3 of the relays as it's going back to Alice. And then you watch all of the different constant rate circuits you've got, and 3 of them slow down. 3 of them get congested because there's other stuff trying to go through those relays, and then you know these are the 3 relays that Alice used. So it doesn't actually break Tor, because the goal of Tor is to prevent somebody from learning that Alice is talking to Bob. And all this attack does is let you learn that somebody is talking to Bob, and here are the 3 relays that she used. So the only missing thing is, where's Alice? Which Alice is it? It's a little bit of a concerning attack, because you're basically bridging the entire Tor network, and all of that distributed trust stuff I talked about at the beginning you can ignore. But it doesn't totally break Tor. But it gets worse. There was a paper in 2007 from Nick Hopper at University of Minnesota who said, okay, step 1, do that attack. Figure out the 3 relays that Alice is using. And then I'm going to build my own circuit through those same 3 relays to the same website. And then I'm going to add up the latencies I'm seeing. I know the latency from me to the entry node. I know the latency from the entry node to the website. So I'm going to do a bit of math, and I end up with the latency from Alice to the entry node. I don't know where Alice is, but I know that she's 75 milliseconds from the entry node. And there are a lot of places that are 75 milliseconds from some place on the internet. So if it's some sort of linkable connection, like you log into Wikipedia, Alice is logging into Wikipedia, every time Alice logs into Wikipedia, you do this attack again. And then you start saying, I don't know where Alice is, but she's 75 milliseconds from here, she's 140 milliseconds from here, and she's 20 milliseconds from here. So then the question is, you consult your handy internet latency routing map, which does not exist, and figure out where she is. You just look her up. Can somebody make one of these handy internet latency routing maps? Probably. Can they do it with enough precision that we can actually say, I bet she's in the Ukraine, I bet she's on the east coast of the US? I have no idea. And then there was a paper just this year by some fellows at Columbia on using bandwidth measurements to do the same sort of attack. So step 1, do the 2005 attack. Figure out what the relays are. And then go to the first relay, and they have a way called a packet train measurement that lets you figure out how much bandwidth there is at any given remote point on the internet. The way it works basically is you dump a bunch of packets on it, and you figure out the timing of bounces coming back. So at that point, they can say, I'm able to detect network flows remotely. So then they consult their handy internet routing map, which doesn't really exist, and then they figure out these are the physical connections from the entry node going back. I'm going to measure each one of them and figure out where the flow is. And once I've gone one hop back on the network, I'm going to do it again. I'm going to figure out the physical connections there. And there are, on average, 15 hops from the entry relay to Alice. So I'm just going to hop back 1 step at a time until I get to Alice. Does it work? There isn't really an internet routing map like that. And they need a 30 kilobyte per second flow sustained for 10 minutes to do the attack. But it's not really clear why they need that. Maybe the attack could get better, and then they'd be even better at figuring it out. So they didn't really break Tor yet, but that makes me kind of concerned. And I'm not really sure how to address that sort of attack, because as you're walking your way closer to Alice, you're getting more information about her. And even if we move the circuit away 10 minutes later, sure, you got somewhat closer to Alice, but you didn't quite get there. But the next time you see Alice log into Wikipedia, you can just start up where you left off and say, I'm pretty sure that this one is going to be the flow, and you just keep walking farther back. So does it work? I don't know. And then there's another paper that should be coming out next year, I hope, by Christian Grothoff and some other people at Denver University. They actually tried to reproduce the original attack, the one where you do the congestion attack and figure out the relays. And they couldn't do it, because when that attack was tried, there were 15 relays and pretty much no users. And now, when there are 1,500 relays and a lot of users, there are 2 problems. One of them is it costs too much bandwidth to actually make a circuit through all 1,500 relays at once. And the other one is there are so many users, there's so much noise, there's so much stuff going back and forth that you can't detect when the congestion is happening, when the clogging is happening. So you can't recognize which relays are being used by Alice. So that That's great. That's good news. That means that the original attack doesn't work anymore. So these other attacks, the 2007 and 2008 attacks, which started with first do that attack, now they're not reasonable anymore because